to go through the related samples t-test from chapter 10, and we'll go through an example, and hopefully I can clarify some things that might seem confusing in the textbook. But we'll go through this, and if you have any questions, please be sure to email me or see me during Cranium Cafe office hours. So let's just talk about the related samples design in general. So remember, specifically when we say a t-test, we're talking about the use of two samples or two groups or two conditions. But the related samples design can be used in a lot of different scenarios, not just with the t-test. So you'll hear related samples design, which means that two scores within the t-test, two scores are obtained for each individual in the sample. Now, that's specific to the t-tests. And in some cases, you might have 3 scores or 4 scores, and that would be a different type of analysis, but it would still be a related samples design. So basically, you have the same individuals being measured on the same thing in multiple different conditions. So the related samples design is called a lot of different things. It's called a within subjects design, a paired samples design, related samples, dependent samples, correlated samples, or repeated measures or repeated samples. So there's a lot of titles used for the related samples design, but in general, a common one is the related samples. So just kind of be aware of when things have the same meaning, because like when you use PSPP or SPSS, which is our statistical software, it refers to related samples as a paired samples. So you'll see that there are some different terms used for the same things. So the key with the related samples design is that the same subjects or same people are used in all of the treatment conditions. That's really the key. So when we consider a related samples, either they're the people in each of the conditions are related or in one way, or they're the same people. So there's often what's called the repeated measures design, which is participants are related or observed in more than one group, and it's usually like a pre and post type of design. But there is kind of this unique design that it's the only time that we actually make sure that we use the correct term, because it is different than a related measures or repeated measures or dependent samples, and it's called a matched samples design. And so that's why we're kind of introducing this idea of, with the related samples, it can be just the same people in more than one group. It could be a pre to post, or it could be just different types of conditions but the same people. Or it could be this very unique type of design where different people are used, but they're matched to where the people in maybe the second group are basically a representative for the person in the first group. So if you ever play baseball or softball, maybe you have a what they call them, a pinch hitter. So maybe your batter is injured, and they have someone that runs for them, runs the bases for them. That's basically kind of like the matched design, to where the people are matched on some kind of characteristics, to where the differences is unrelated to characteristic traits. It's specifically based upon the independent variable. And these can be matched experimentally or naturally, and we'll talk about that. So there's 2 types of very common related samples design. So these are the ones that fall into the typical. So when I look back, I'm looking at related in 2 ways, that same people in more than one group, or if they're matched. So we're talking about 2 different ways, non-matched. So you have that pre to post design. So you have measuring one dependent variable, and it is one dependent variable is being measured specifically on the same participants in like a pre and post type of treatment. So maybe prior to some kind of a training camp for athletes, and then after a training camp for athletes. Sorry about my phone going off, I was being distracted there. And so, and they're measuring the dependent variable as athletic performance. So there's this pre and post design. And these are often called repeated measures designs or repeated measure t-tests if there's only two conditions. But it's also the same thing if you say related samples design, so same thing. Then there's the within subjects design, and this is really even a pre to post is a within subjects, because these are all really within subjects designs, meaning the same people. But truly a within subjects is often not very specific as far as a pre and post. So it might just be that you have several conditions, and it's not necessarily before a condition and after a condition. So for example, you might be testing memory after aerobic exercise and then after anaerobic exercise. So it's not a before and after. These are both after exercise, but two different types of exercise. So it's not necessarily pre and post. The nice thing about these types of designs is that they're really, as far as statistical analysis goes, they're done the same way. It's just a different way of coming up to the same types of results. And so this is information you might want to know to be able to determine whether a research scenario you're provided is a related samples design, or whether it is an independent t-test. So either participants are pre and post, or they're the same participants in different conditions. Either way, they're a related samples design. So here's that unusual design that I was talking about, which is called a matched pairs design. So this one, if I was to give you a research scenario and you told me this was a related measures t-test, you'd be wrong, because specifically we have to state that it's a matched pairs design, because ultimately we're using different people, but they're matched either through experimental manipulation or a natural occurrence. So experimental manipulation would be where the researcher measures some traits or characteristics and then matches the conditions, the participants in each of the conditions based upon those measurements. So like, let's say you're measuring intelligence, then you match the two participants scoring the highest, the two scoring the next highest, and so on, and you match them. They're different participants in each of those conditions, but they're matched on some characteristic that makes the, let's say, person in the condition 2 basically be a stand-in for the person in condition 1. But there's also matching through natural occurrence, which is actually probably what you've heard of the most in psychological research, which is based on genetics. So biological twins, they're matched genetically. So yes, they're two different people, but they're matched genetically. So that would be a matched pairs design. The interesting thing is we need to be really careful that we're stating that it's a matched pairs design, but beyond that, as far as calculating the analysis, it is exactly the same as the related measures t-test. So there would be no difference in calculations. It's just we need to be careful that we're stating that we're using this particular matched design. So there are some real advantages for conducting a related samples test, any of the related samples. So it is often much easier to come up with 30 participants to participate in two different conditions than it is 30 participants to participate in one condition and then another 30 to participate in another condition, meaning you have to have 60 participants. So it's a little bit more practical. It's much easier to get 30 participants than it is to get 60 participants. And so, as you know, our goal is to reach 30 because we know that samples become normally distributed as we hit 30 or greater. So that's a little bit more practical as far as being able to get that many people. The related samples, we're talking about minimizing our error, because remember, in the equation alone for error, so if we just think of S of M, okay, we have our standard deviation divided by the square root of n. We are minimizing the standard deviation because it's the same people. So there's not going to be a great deal of variance between the two participants just based upon characteristic traits, because we're using the same people. So it decreases that standard deviation, so it decreases this overall error. And then it increases the power. Because of the fact that we're reducing the error, we are increasing the t statistic. So if you remember, we have, basically our error is in the denominator, and then our mean difference is in the numerator. Well, if we decrease this number, the error, that means a lower number goes into this, meaning this t obtained will be larger. So it increases power, because remember, power is the likelihood of finding significance or rejecting the null. So there are some real advantages for selecting the related samples tests. So here is what our related samples t-test looks like. Now, this really ultimately is the same exact thing as a one sample t-test, except that now you're coming up with the mean difference and you're coming up with the estimated standard error of the mean difference. Now, this mu of d is our null. This is the null. And in this case, if you remember with the one sample t-test, we were given the population mean. Well, in this case, and the population mean was the null, but in this case, our null is that there is no change, right? Which is equal to 0. So 0. So that's always going to be 0 when we're dealing with a related samples design. That mu of d is our null, so it's 0. And then if you'll notice, we have m subtext d and then smd. And basically is what we're doing is to get these, we're gonna have to start right here. And we're gonna have to get the difference scores. So basically we're gonna have to subtract every one of our pre-test scores from the post-test scores and get the differences. Once we get the differences, we can calculate our mean of the differences. So I'll show you what this looks like. So here we have, again, our mu of d, which would be 0. So there would be no difference, right? If we're really sane in the population, there would be no difference. That's really what the mu of d would be based upon the null. So is what we have to do, and so here we have like this basic setup. Like here's our pre, here's our post, okay? This is where it gets confusing, because no matter what, whenever I give you data, I will always give you pre and in this group and then post here. But as Americans and many countries, we like to do things from the left to right. But in this case, if we went left to right, it would be 10 minus 14. Remember, because we're doing x2 minus x1 to get the difference. If we didn't do that and we just went left to right, this would have been a -4. The person B would have been a +2 if we went left to right. So is what we need to do is show, are the scores going up or are they going down for that post? And in this case, they went up by 4, right? 4 points, because this is larger than this. 14 is larger than 10. This went down by 2. This person went up by 3. This went down by 1, or up by 1, sorry, up by 1. And then once we get those differences, we're basically going to ignore the original data and just work with our differences. So that means we're going to add everything up. 4 minus 2 plus 3 plus 1. So we'd have 4 minus 2 is 2, plus 3 is 5, plus 1 is 6. So our sum of D equals 6. And we would literally go through the same steps as normal, getting all of the information. So getting all of the calculations. So if we want the mean of our differences, we're going to take that sum of D and divide by N. Now I like to put like a little low subtext D so that we know it's the N of the differences. So basically, or how many people are involved or how many different scores are, and there's only 4. So in this case, it'd be 6 divided by 4 would be how we would get our mean of the differences. So here's the overall breakdown. So we just figured out how to do this. We know that this is equal to 0 in the related t-test. And then we're going to do things like get the standard deviation of the differences, meaning that we're going to need to get the sum of D and the sum of D squared, right? So if we were to go back, we would also have to come up with this D squared on each of these. So we would have 16, we would have 4, we would have 9, and we'd have 1. And then we'd add those up. Now, reminder, for many of you, your calculators, if you put it in as just like say -2 squared, it's going to hold the negative. Whenever we square a negative, it should be a positive number. So make sure that you're not just automatically taking your calculator as being correct, because that's not necessarily true. So I always say if you square a negative number, just put it in as a positive and drop that negative. So all of that is kind of needed so that you can get the sums of square of D. And remember this N, put that little subtext D there, it's N of the differences. So it's the sample of the size of the differences. And then we're going to get all that to get our standard deviation of the differences. So we plug that in here. And so that we could get our estimated standard error of the differences, which goes into our denominator. It's really precisely exactly, once you get the differences, once you get these here, these different scores, you're basically going to conduct a one sample t-test once you have that. So with the related samples t-tests, a little bit different than the independent t in regards to the assumptions. It's very similar to the one sample t-test in regards to the critical value and the degrees of freedom. So again, think N of D when you're looking for your degrees of freedom for the critical value. You're going to use how many different scores there are, -1. And then when it comes to assumptions, we now only really have 2 major assumptions. There's always random sampling as well, but 2 assumptions you really need to be aware of, and that's normality and what's called independence within groups. So normality, as you know, there's 2 different ways you can get normality. You either make sure your sample size is 30 or greater, or you make sure that you take your sample from a normal population distribution. The second thing is independence within groups. So the independent t-test was independence between groups. This is independence within groups. So basically, none of the scores from the participants were affected by the other people within the groups. So there's no influence within each of the group or treatment. Now we know that the scores from, say, the post-treatment are going to be influenced by the pre-treatment. Let's say we're talking about depression. If you go into something with high depression, it's going to influence how high your depression is after treatment. So there is not independence between, but within the group, you know, Sam is not influencing Sarah's depression score. So the people within the treatment groups are independent from one another. So here is an example of a hypothesis test. So we'll kind of go through this and pick this apart. So researchers testing the effects of a new medication. In order to test whether there's a difference, she obtained 4 participants and measured for their strength scores prior to medication and then again after taking the medication for 1 month. So basically the prior and after are independent, like our conditions, and then, you know, prior to medication, after medication, and then the strength is the dependent variable. Okay, and it says just testing the effects. So if you really think about that, that's pretty vague. Nowhere in here is she saying that the strength will go up or the strength will go down, anything like that. It's just saying they're testing the effects. And so then we give the criteria of 0.05. So the key is looking through, don't make assumptions. So I've noticed a lot of students make assumptions because maybe the research scenario is testing something that seems like it would have an obvious direction. Like it would obviously have an increase. Just because you think it seems obvious doesn't mean that's how the researcher's testing it. So make sure you stick to these research scenarios and test it either as a 2-tailed test as stated or a 1-tailed test as stated. Don't make assumptions that aren't there. Unless you're doing your own research, then you could make your assumptions. But since these aren't your research hypotheses, you have to go with what's already given to you. Okay, so here is the data from that. Here we have the before and the after with the strength scores. So is what we would need to do is go through and get our differences, right, for each of these. So if you look, this went down by what, 5 points, right? 5, right? So that's what you want to do is make sure, but this one went up, right? So we want to make sure that you're going through these very carefully and getting the right direction in these. So 242 minus 221 is up by 21 points. So that's a positive. And then 219 minus 196 is up by 23 points, right? 228 minus 203 is up by 25 points. So you want to make sure that you're going the right direction, because let's say all the scores go down, but if you're showing positives on all these, then you're going to suggest that scores went up rather than going down. So here's what we have for step 1. So the step 1 of hypothesis testing is basically you're going to make sure you have a clear indication of what your independent variable is, your dependent variable, and whether there's direction or not. So there was no direction given. So all I put is there is not a significant difference in strength after taking a new medication. And remember, some of you are still mixing this up. H of O is the null, which means that there's not something happening. H of 1 is the alternative. There is something happening, okay? And as you can see, we're keeping it vague. you could say not an effect in strength, or not influencing strength. So whatever it is, it's just as long as you're not putting a direction, because the researcher never stated direction. And then step 2, we're going to get that criteria, setting the criteria. So taking your alpha, which is 0.05, and we're going to make it to tell. So if you look up the degrees of freedom, so we had 4 different scores, 4 scores minus 1, our degrees of freedom is 3. If you look that up, 0.05 to tell, your critical value is 3.182. Now you should be reporting one of 2 different ways. Either you report it T critical value equals positive negative 3.182, or you could put T critical value equals 3.182 and write to tell after it. But it has to state one way or another that you're seeing that it's both sides. So here we have a distribution. Here's where it's significant, or here's where it's significant. It's going to go one way or the other, in one direction or the other. We just don't know which direction. So here's those basic calculations. So we're going to get our differences. So like I said before, this person, their score, their strength went down, but everyone else's went up. So when we add these up, we get the sum of D equals 64. And then I'm going to get that mean difference. So meaning I'm going to do the sum of D divided by N for that mean difference. So I put, 64 divided by 4. That gave me 16. Then I'm going to square each of the differences. Now, this is where, again, you have to be careful, because if a lot of you, if you plug -5 in your calculator and square it, you end up with a -25. Well, that's not right. If you square a negative, it should be positive. So be really careful about that. So you're squaring each of those scores to get your sum of the D squared, sum of the differences squared. And then you're going to get your sum of D total squared. So this right here, sum of D squared, is the same thing as if I put 64 squared. So basically it's this sum of D squared, which is 4,096. So these are kind of the basic calculations you're going to need to get that related t-test. So here's kind of how I went about that. So we had the sum of D squared, which was 1620, minus sum of D total squared, which is 4096, divided by N. And this could be the ND. Those are used interchangeably. So the whole thing is how many scores, how many observations were there, or how many differences between the observations were there. So 4 differences. So our sums of squares is 596. So we can plug that into our standard deviation equation. This is where we need to put that degrees of freedom. Remember, here's the standard deviation equation. So that's the only time we're going to use that -1. Standard deviation is 14.09. Now, we use that to get our estimated standard error of the differences, 14.09 divided by the square root of 4, because that's the sample size. So our estimated standard error is 7.045. So we have everything we need now to calculate that related samples t-test. Because we already have this, and if you remember, this is always going to be 0 for that related samples t-test. So plugging it in, here we have that 16 minus 0 divided by 7.045. And we end up with a t obtained of 2.27. Now, at this point, we can compare and see, did we find significance? Well, here we look over here, and I have the distribution for you. So we're using that criteria, the critical value of -3.182 and +3.182. Remember, right down the middle ultimately is 0. So anything to the left is negative, anything to the right is positive. Our test statistic was 2.27, which fell to the right of 0, but it did not fall beyond our critical value. So we did not reject the null, we're retaining the null. So if you'll notice, basically this little bubble is giving us anything from here to here. So any of this region from the critical value boundaries, all that entire area in the middle, our probability value, our p-value is greater than alpha. That's how we know. Anything out here in the corners or at the tails of the distributions, we know that p is less than. And so just think of p as being how big something is, how much is pushed into there. There's a lot of data in this region, so p would be large. There's very little data over here, so p would be small. Think of it that way, maybe. Different ways of trying to kind of navigate that thought process. But we're not done yet. So, okay, we know our test isn't significant, but we still have things we have to do. So we need to calculate an effect size. There's two different types of effect size that we could calculate. There's the Cohen's d or eta squared. So those are the two that I'm giving you options to calculate. I mean, if you really want to calculate omega squared, which was introduced in the chapters, you can. But I really am only providing these two so that you can kind of keep them straight. And I really want you to know what they're measuring. So with Cohen's d, we're talking about how many standard deviations did the treatment affect the dependent variable. So with the estimated Cohen's d, we're taking the mean difference, 16, and dividing by the standard deviation, 14.09. So in this case, our d equals 1.14. Well, that is a large Cohen's d. That means that basically the sample mean shifted by 1.14 standard deviations, okay? So it was a pretty large shift. Our eta squared, now we're gonna be using the t obtains, and this is one of the reasons why I say I recommend your Cohen's d, because if you get your test statistic wrong, then you get your effect size wrong too. So Cohen's d gives you kind of a second chance for getting more points. So your t obtained squared divided by the t obtained squared plus degrees of freedom. When I put this in my calculator, I usually put parentheses around this. I always do, so that you can make sure you're not ending up just dividing the t obtains by each other. So in this case, eta squared is 0.61, meaning 61% of the variability in the strength measurement was due to the medication. That's a lot, 61% is. So that's really what I want you to know is what are those used for, and then how to calculate at least one of them for your APA result. So the next thing we need to do is calculate the confidence interval. So in this case, we're going to just do like we did with the one sample t. We're going to use our sample mean to estimate the population parameters. This t is always a t critical value for 2 tell. Doesn't matter whether the original test was 1 tell or not, you always plug in a 2 tell. Luckily for us, it was a 2 tell, so we don't have to look up another one. And then our estimated standard error, which is 7.045. So once we calculate those two, we should be getting negative 6.42 is the lower boundary, and then 38.42 is the positive boundary. Now I'm gonna kind of talk to you about what does this mean? Because I think that's probably one of the biggest questions I get from students is like, what is this useful for? Well, we're estimating what the population parameters would be if the null is true. So let's look at, so we're actually testing the null hypothesis. And the null hypothesis, it states there will be no difference, right? No significant difference. If we say no difference, that's the same thing as saying 0. So if that null is true, 0 would fall in between those boundaries. But if we found significance, 0 would fall outside of those. So we have our lower boundary is -6.42. You notice here, our upper boundary is 38.42. Well, our null, which is 0, falls in between there. So we did not find significance. It's another way for us understanding the data. It's another way for us to like kind of confirm, okay, yeah, our when we looked at our critical value compared to our test statistic, if we determined that there was no significance, this is another way of showing us, yeah, there was no significance. But it's also another way for us to know, okay, wait a minute, maybe I should have used a different alpha level, because 0 is pretty close to -6.42 compared to 38.42. So this is pretty close to this boundary. Let's just put it that way. If it's real close to the boundary, it's possible that you made an error. And in this case, it's possible we made a type 2 error because we retained the null, meaning that maybe our alpha level was too stringent. Now you're going, but wait a minute, we used 0.05. Right, we used 0.05, but 0.05 to tell. And so if we would have used 0.051 tell, then it very likely would have been significant. So I'll even look it up. Like if we would have used 0.051 tell, now our degrees of freedom was 3, 0.051 tell would have been 2.353. In actuality, let's go back, 2.3 still would not have been significant, but it would have been closer to being significant. So it gives us some ideas to seeing like, okay, are we using the right alpha level? Was it a type 1 or type 2 error? Well, it probably wasn't a type 2 error, but more than likely, it was a lack of power. Because if you look, these effect sizes are huge, huge effect sizes, but we only had 4 people, 4 participants, so we lacked power. So that tells us something. It's probably affected less by error and more by a very small sample size. So this gives us some extra information. So here's our APA results for those, for the related samples T. So in this case, there was not a significant difference in strength after taking the new medication. We report T, degrees of freedom are obtained T. P is greater than 0.05 because it was not significant. We tested 2 tell. We report our Cohen's d and our 95% confidence interval. Remember, we never report our critical value, and it has to be within this order of information for APA results. It's a key component to communicating research. It is a language, definitely a language. So let's look at really quick a couple of questions. So if you email me the answers to these questions, you can get some extra credit points. So the first one is, which of the following would be a repeated measures test or related measures, related samples, and which would be a matched subjects? So which one would be a repeated measures and which would be a matched subject? So group A, there's a group of identical twins is tested for IQ. B, comparing boys and girls' strength at age 3. C, evaluating the difference in self-esteem between athletes and non-athletes. And D, students' knowledge is tested in September and December. So let me know which one of those would be repeated measures and which one would be a matched subjects design via email. But you have one more. Tell me whether each of these is true or false. So the first one is, a matched sample study requires only 20 participants to obtain 20 scores in each of the conditions being prepared or compared. Is that true or false? And then the second, As the variance of the different scores increases, the magnitude of the t-statistic decreases. True or false? So shoot me an email with your responses to those two learning checks and earn yourself some extra credit points. And please don't hesitate to pop into my office hours on Cranium and ask questions, or shoot me an email with any clarification you may need regarding the related samples t-tests. Have a good one.